Making nanoparticles is only half the battle. The real question is, how do you know what you've made? Size, shape, surface charge, optical properties, everything must be characterized. In this video, we'll break down the top to most used techniques to characterize nanoparticles in any lab. Welcome back to the channel. If you're a student, researcher, or just a nanotech enthusiast, this is the video you need. Whether you're synthesizing gold nanoparticles, silver, iron oxide, or any quantum dots, characterization is the only way to prove what you've made is what you intended. Today, we're explaining 3 powerhouse techniques you'll find in nearly every nanotechnology paper and lab. DLS, dynamic light scattering. SEM, scanning electron microscopy.
So, how do scientists characterize or study nanoparticles? There are a few key ways. Electron microscopes give us super detailed images, letting us see their shape and size. X-ray diffraction reveals how their atoms stack up, kind of like peeking at the blueprint of a building. And dynamic light scattering? That helps us measure how they move around in liquids. But it doesn't stop there. Scientists also check what nanoparticles are made of, how they react with other stuff, and even how they interact with living things. All these tests help us use nanoparticles safely in everything from medicine to electronics. So next time you hear about nanoparticles, remember, there's a whole world of science making sure they do their job, even if you can't see them.
Everybody is looking for the tiniest details in science. But what if those details are smaller than a wavelength of light? That's where DLS comes in. DLS is all about shining a laser through a solution and watching how the light scatters. Think of it like using a flashlight in the fog. The way the light bounces helps reveal the size of those invisible particles. By analyzing how the scattered light changes over time, DLS can tell us the average size and even the size distribution of particles as small as a few nanometers.
Here's how it works. Let's keep it simple. Dynamic light scattering, DLS for short, is a technique scientists use to measure the size of really small particles in a liquid. Think nanometers, way smaller than the width of a human hair. Here's what happens. First, you shine a laser beam right through your sample. As the light hits those tiny particles, it scatters in all directions. But here's the cool part. The particles are constantly jiggling around because of Brownian motion, so the scattered light isn't steady. A detector picks up that scattered light, and the intensity keeps flickering over time. By analyzing how quickly those flickers change, a computer can figure out how fast the particles are moving. And since smaller particles move faster than larger ones, we can calculate their size.
So, what exactly do you get from a dynamic light scattering or DLS experiment? The main output is a graph showing the distribution of particle sizes in your sample. Think of it as a size fingerprint. DLS works by shining a laser through tiny particles suspended in liquid. As the particles move, they scatter the light in patterns that reveal their size. The software crunches all that data and gives you a peak, or several peaks, representing different particle populations. You'll also see numbers like z-average for average size, and a polydispersity index that tells you how uniform your sample is.
DLS, dynamic light scattering. It's the go-to technique to measure hydrodynamic size and polydispersity index, PDI, of nanoparticles suspended in a liquid.
Imagine you're trying to study nanoparticles, those super tiny bits that are everywhere from medicine to makeup. Regular microscopes just can't cut it. Enter SEM, or scanning electron microscopy. Instead of light, SEM uses a focused beam of electrons to scan the surface of your sample. These electrons bounce off and give us insanely detailed 3D-like images down to the nanometer scale. Not only can you see individual particles, but you can also measure their size, shape, and even spot how they're grouped together. Want to know what your nanoparticles are made of? SEM's got you covered with elemental analysis, too.
So imagine a regular microscope. It uses light to magnify things, but there's a limit to how much detail you can see. SEM flips the script by using electrons instead of light. Here's how it works. First, you place your sample inside a vacuum chamber. Why? Because electrons don't play well with air. They need a clear path. Then, a superfine beam of electrons is fired at the sample from above, kind of like a supercharged flashlight, but with particles millions of times smaller than dust. As these electrons hit the surface, they bounce off in all sorts of ways. Some electrons scatter, some knock loose even tinier electrons from the sample. And these escaping electrons are what the microscope actually detects. Think of it as a digital game of billiards, with electrons ricocheting everywhere. Next, detectors gather all these signals and translate them into a crisp black and white image. The result? You get jaw-dropping surface detail, like seeing every hair on a fly's leg or the ridges of a silicon chip. And the best part, SEM images can magnify up to hundreds of thousands of times. That's like zooming in so close you could spot a fingerprint on an ant's foot. So the next time you spot one of those epic microscopic images online, just remember, it's not magic, it's science, and it's totally electrifying. If you're curious about how SEM changes the way we see the world, let me know in the comments and don't forget to subscribe for more science adventures.